Okay, so now we are going to talk about perfect graphs. So I think I mentioned before that, maybe we talked about perfect graphs earlier, but thinking about it now, I'm fairly certain that we have, in fact, not talked about perfect graphs or brought them up yet. So now is the time to do so. So graph G is perfect if for all possible, so G is perfect if, let's say, the chromatic number of H equals the clique number of H for all H, which are subgraphs of G. So in other words, for any possible subgraph of G, the chromatic number, instead of just being bounded by the size of the largest clique within that subgraph, is exactly equal to the size of the largest clique within that subgraph. And here, unlike color critical graphs, we aren't having the disclaimer, I guess, that H is also not isomorphic to G. But one thing we should specify, H is an induced subgraph. So, I'm thinking about it just now. I'm fairly certain that I've mentioned inducing subgraphs multiple times. I know I've talked about it. A couple of you have asked specifically about it, but I don't think I've formally defined the difference between induced and non-induced subgraphs. So I'll just define it now. An induced subgraph, to put it simply, it's a subgraph comprised of some subset of vertices of some G, and here's the important part, all edges between those vertices. So we'll draw an example in a second, and then we have also a non-induced, where effectively, to put it simply, graph containing a subset of edges. So if we would consider, say, our graph G here, let's make it a little more complex. So something like that. Let's say we can have induced subgraph if we're considering some vertex set S here. We can have our induced subgraph containing all edges, or a non-induced subgraph containing some subset. So if we're considering S being the vertices that we've kind of circled there, those three vertices, an induced subgraph considering that vertex set S will contain all edges between all those vertices, whereas a non-induced subgraph will not necessarily contain all edges. In effect, inducing essentially implies that we're essentially bringing all edges along with us for the ride. Maybe one way to put it, maybe not the best way to put it, but it's a way to put it. So that's just an important distinction that we should bring up right now specifically. So let's talk about perfect graphs here a little bit. So what graphs are perfect? Well, all cliques are in fact perfect. So if we consider some arbitrary clique here, let's just make it K4 for simplicity. Obviously, if we induce on any subset of edges, we are going to end up, or some subset of vertices, we are going to end up with a clique because we're bringing along all edges for the ride, in effect. So all cliques are in fact perfect because if we consider our G here, we can color that in exactly 4 colors, or induced subgraph on 3 vertices, irregardless of which 3 vertices we select is going to be isomorphic to each other. It's just going to be a triangle, which is also a clique, which is also, essentially the chromatic number is equal to the cardinality of the vertex set there, and then same thing for 2 vertices and 1 vertex. Something that isn't as intuitive, all bipartite graphs are perfect. And if we consider any arbitrary bipartite graph, I don't know, something however we want to draw it with our x, y, so our g, x, y here. The largest clique is always K2, irregardless of what vertex set we select to induce a subgraph on, and we can always color with, let's say, with 2 colors. Again, irregardless of what subgraph we select, and since trees are bipartite, obviously they're going to be perfect as well. So one more class of graphs, kind of tying this all together, is chordal graphs. Chordal graphs are perfect. So let's make this its own little thing down here because we're going to do a little bit fairly short proof to demonstrate this case. So chordal graphs in general are perfect. What we saw before is the leading vertices from a chordal graph. So in our previous proof we saw this, the leading vertices from a chordal graph results in a chordal graph. Again, because we can't just delete a single chord from a cycle by removing a vertex, because if we remove that vertex, we're going to essentially delete that cycle along with whatever chords that vertex contributed to that cycle that we're considering. So what we're going to do is show essentially what we're going to do is show that the chromatic number G equals the clique number of G for all chordal graphs. And so since a perfect graph is, by our definition, we considered induced subgraphs. So essentially when we're taking an induced subgraph, we can get there just by deleting vertices from our original graph. So if our original graph is chordal, then obviously any induced subgraph of that graph is correspondingly going to be chordal because, again, deleting vertices can get us to any induced subgraph from our original graph, and deleting vertices cannot introduce a chordless cycle. So from what we saw before, if we're considering some G, we note that G has a simplicial elimination ordering. So again, we just proved that before, earlier in class, that a chordal graph will have a simplicial elimination ordering. So if we consider some G, let's specify G is chordal. then G has a simplicial elimination ordering. So let's consider that ordering in reverse order. So going back to previous class, we talked about the simplicial elimination orderings. The way we defined it was a little, weird because we kind of defined it in a certain order, then kind of considered it in that reverse order. So, we did that in the context of the greedy coloring algorithm. And we're going to do that in pretty much the same context right now. So if we consider that simplicial elimination ordering in reverse ordering as some VI is added back, create that GI. The neighborhood of that VI is a clique. And then from here, we can just consider greedy coloring. And so, what does that mean? Essentially, I think we can all see where this is going. If that VI gets color K, essentially, we know it is in a clique of size K. So its neighborhood is a clique of size K minus 1 by adding VI, attaching it to all of its neighbors. We construct a clique of size K, and we can color our vertex VI with color K. Clique is. And then essentially we can repeat for all potentially VI within the vertex set of G, etc., etc. And what does that give us? That gives us essentially a coloring where the max color is equal to that max clique. And so note here, something else we can note, just kind of tying it back to some stuff we talked about before. Optimal order for greedy coloring. So that simplicial elimination ordering correspondingly also gives us an optimal ordering as well. If we consider it in reverse ordering, consider coloring it in that way. So for next class, we're going to move on to planarity, planar graphs, all that good stuff. So leaving coloring behind, there's a lot more interesting stuff we could talk about with coloring. Out of all the graph theory kind of things, like the more theoretical side of things, like graph coloring is probably one of the most well studied, if not the most. If there was, a second maybe most well studied, it might be, say, from the purely theoretical side, like graph planarity maybe. So these two, like I said before, these two are kind of like this half of the class is the pretty theory heavy side of things, just because talking about graph coloring, which a million different things we could talk about, a million different proofs related to them, and planarity as well, like some of the more well-known proofs kind of combine the two concepts between planar graphs and graph coloring. So we'll get to those in the coming